Hello students, I am Professor Anindo Das from Achievers and welcome to my lecture series on second law of thermodynamics. So our topic is second law of thermodynamics. Students, second law of thermodynamics is one of the most important topics in the realm of physical chemistry, or you can say in the realm of entire physics. It is the most important topic. Second law of thermodynamics is basically the guiding subtopic which will dictate the fate of any physico-chemical process. Whether a physico-chemical process is going to occur in nature or not, that will be dictated by second law of thermodynamics. So it is of immense importance in context to the physical chemistry, or you can say in context to physics. Okay, so we'll move on to this particular topic, the second law of thermodynamics, and we would explore a lot of natural phenomenon in context to this second law of thermodynamics. Okay. Now, in today's lecture, we would deal with engines and refrigerator. So today's lecture is all about engines and refrigerators. It's all about engines and refrigerators. In this context, we'll study Kelvin Planck statement. And Clausius statement. So in context to engines and refrigerators, we'll study these two important statements. They are the fundamental statements in context to the second law of thermodynamics. So this is our very first topic, the concept of engines and refrigerators. This is our very first topic, the concept of engines and refrigerators. And in order to understand the concept of engines and refrigerators, the working of engines and refrigerators, we must be acquainted with these two important laws, the Kelvin Planck statement and the Clausius statement. So these are the very fundamental or rudimentary statements in context to the second law of thermodynamics. Okay. Now, students, let me make you clear that this particular statement, the Kelvin Planck statement, in short we will write it as Kp. This Kp is connected to engines. Engines are understood in terms of this Kelvin Planck statement. And the Clausius statement is in short written as C. And C is understood, the refrigerators are understood in terms of C. So, in this particular topic, we would be exploring the engines and the refrigerators. And in order to understand the working principle of an engine, we must be acquainted with the Kelvin Planck statement. And in order to understand the working principle of a refrigerator, we must be acquainted with the Clausius statement. Okay. So, our very first lecture on the second law of thermodynamics is all about the exploration of engines and refrigerators in context to Kelvin Planck and Clausius statements. Okay. So at first, let us move on to the Kelvin Planck statement, in short which will be written as Kp. Now, before writing down this statement blankly, we must understand how does an engine work. If we understand that simple free diagram of an engine, then we can write this law very easily from that free diagram. Okay. So at first, we would acquaint ourselves to the free diagram of an engine, and after that, what we'll be doing? We'll be dealing with the statement, the fundamental or the formal statement given by Kelvin and Planck. So, before that, we must be acquainted with some important terms. What is a reservoir? What is a reservoir in thermodynamics? What is a reservoir? What is a reservoir? Now, in thermodynamics, we define reservoir in a typical manner. In thermodynamics, we define reservoirs in a typical manner. How do we do so? Suppose we have two different bodies. Say this is A and this is B. And say A is hotter than B. Now what if we allow A and B to come in contact with each other? What will happen if A and B come in contact with each other? If they come in contact with each other, then what will happen? There will be a flow of heat from the high temperature body to the low temperature body. A is of higher temperature, B is of lower temperature. So naturally there will be a flow of heat from A, the one with higher temperature, towards B, the one with lower temperature. Now what will happen then? You'll see, say A has a temperature of this much amount and B has a temperature of this much amount. Now what will happen? There is a heat flow from A to B. So what will happen? A will gradually lose temperature, it will be cooled down, and on the contrary, B will get heated up, and eventually they will reach a temperature where both A and B will be under the state of thermal equilibrium. That means both A and B will possess same temperature. That is said to be the state of thermal equilibrium. The temperature corresponding to thermal equilibrium will be lower than the hotter body, that is A, and will be greater than the colder body, that is B. That is quite natural. This much of thermodynamics or this much of principle of heat is already known to all of us. We are already acquainted with these facts. Now what will happen? What will happen if you replace one body by a reservoir? Actually, reservoirs are considered to be large collection of heat. Reservoirs are considered to be large collection of heat. So what will happen if A is a hot reservoir and B is a cold body, and you allow B to come in contact with the reservoir, then again by the principle of calorimetry there will be a flow of heat from the region of higher temperature, that is from the hot reservoir, to the colder body. But in this case, the thermal equilibrium temperature will be a bit different. It will happen so that the colder body will eventually undergo a rise in temperature, and at the state of thermal equilibrium it will reach the temperature of the reservoir. And the reservoirs will never lose any temperature. Actually, reservoirs are considered to be large collection of heat. So if you withdraw heat from the reservoir, or if you pour heat into the reservoir, there will be no change in temperature. That's what is the speciality of a reservoir in context to thermodynamics. In context to thermodynamics, we understand reservoirs as a large collection of heat. It's so large that if you withdraw some amount of heat, or if you pour some amount of heat into the reservoir, then there will be no change in temperature. It's like an ocean of heat. It's like an ocean of heat. Now just think, if you withdraw a bucket of water from ocean, or if you pour a bucket of water into ocean, then what will happen to the ocean? Will there be any change? Will there be any change? The answer is a big no. There will be no change. Similarly, a reservoir will behave. A reservoir is actually a large collection of heat. It's a thermodynamic entity. It's a large collection of heat. So if you allow any heat flow towards the reservoir or away from the reservoir, there will be no change in temperature. So the reservoirs are always under isothermal condition, that is, it will maintain constancy of temperature. So what we know about reservoirs? Large collection of heat, large collection of heat, large collection of heat. It's basically a system. A system. Reservoir is a system. It's a large collection of heat, first of all. Secondly, no change in temperature with inflow or outflow of heat. No change in temperature with inflow or outflow of heat. That's what we understand about a reservoir. That's what we understand about a reservoir. Okay? Okay? So this is a large collection of heat, and there is no change in temperature with inflow or outflow of heat. Okay? So how can we construct an engine? The free diagram of engine looks like this, you see. You have one hot reservoir maintained at high temperature TH, and you have a cold reservoir maintained at low temperature TC. Okay. HR is the hot reservoir. It is maintained at a higher temperature TH, and CR is the cold reservoir. It is maintained at a lower Kelvin temperature TC. Now these two thermodynamic entities are connected by an engine like this. This engine works in a cycle. Works in a cycle. This engine will work in a cycle. E stands for an engine, and this engine will work in a cycle. Now, what is the purpose of an engine? What is the purpose of an engine? The engine will withdraw heat from the hot reservoir and convert it into work. That is the sole purpose of an engine. The purpose of an engine is to withdraw heat, from the hot reservoir and convert it into work. Because heat and work are both forms of energy. So what will an engine do? It will withdraw heat. It will withdraw heat from the hot reservoir. So QH amount of heat is withdrawn from the hot reservoir, and it is converted into work. So W cyclic amount of work is done by the engine. The engine works in a cycle. That's why we have written CY. CY stands for cyclic. So QH amount of heat will be withdrawn from the hot reservoir, and eventually that will be converted into work. But Kelvin Planck statement says that An engine cannot convert the entire amount of heat into work. An engine is incapable of converting the entire amount of heat withdrawn from the hot reservoir into work. That means QH cannot be entirely converted into W cyclic. QH cannot be entirely converted into W cyclic. A part of QH has to be rejected to the cold reservoir, and that is written as QC. So at first let us write the definition, then again we'll interpret this. So according to Kelvin Planck statement, an engine, it is impossible for an engine to withdraw heat from the hot reservoir and convert it entirely into work without rejecting a part of it to the cold reservoir. Let us read out the statement. It is impossible for an engine to withdraw heat from the hot reservoir and convert it entirely into work. That means the heat withdrawn from the hot reservoir, that is QH, cannot be entirely converted into work. That means QH cannot be entirely converted into W cyclic. Magnitude of QH can never be equal to magnitude of W cyclic. It can never happen so. It has to reject a part of heat to the cold reservoir. So this QC must be non-zero. That means a part of heat has to be rejected to the cold reservoir. This is the statement given by the Kelvin, given by this two scientists, Kelvin and Planck. So this Kelvin Planck statement interprets the nuances or the working principle of an engine. Okay. So we have understood how an engine works and what is the fundamental criteria that has to be satisfied by an engine in order to be feasible in nature. We have understood the criteria of viability of an engine. That is well understood to all of us. Now, we would apply first law of thermodynamics and arrive at the efficiency of an engine. It is one of the most fundamental parameters in context to an engine. So in this context, what we'll be doing? We'll be defining the efficiency of an engine. Let us remove this concept of reservoir. We have understood what is a reservoir. So our present concern is to understand the meaning of efficiency. Efficiency of engine is denoted as eta. It is denoted by the Greek letter eta. And by definition, eta is basically the amount of output divided by the amount of input. It's output by input. It's what we are getting divided by what we are giving. What we are getting is the output and what we are giving is the input. So in the numerator you will have what we are getting. That's the output. The output is what? Mod W cyclic. So this is the output. And what we are giving? We are giving mod QH. Mod QH is being given to the engine. So mod QH will be there in the denominator. So mod W cyclic is basically the output, and mod QH is basically the input. So it's a ratio. It's a ratio of two quantities, both of which are dimensionally equal to energy. Okay, both the numerators and denominators are dimensionally equal to energy, and that makes eta to be an unitless parameter. An unitless parameter. So this is how we define eta. This is how we define eta or efficiency. This is a very important parameter in context to an engine, and nonetheless in context to the second law of thermodynamics. Now we'll try to evaluate some other expressions of eta as well. For that purpose, we need to apply the first law of thermodynamics. So, according to first law of thermodynamics, we know that W cyclic plus Q cyclic is always equal to 0. This is the fundamental statement of first law of thermodynamics. This is the fundamental statement of first law. This is the fundamental statement of first law. Q cyclic plus W cyclic has to be 0. Q cyclic plus W cyclic has to be 0. This is the fundamental statement of first law. Now, we would analyze everything with respect to an engine. Because here engine is our reference. This is our reference. Here engine is our reference. So we'll analyze all the thermodynamic parameters with respect to E. So with respect to E, what I can see, QH is positive because the arrow of QH is towards the engine. The arrow of QH is towards the engine. That means the engine is gaining in QH. So QH has to be positive. So you can say QH is equal to mod QH. It's positive. The arrow is towards the engine. That means heat is gained by the engine. So QH is the heat gained by the engine. So the engine is gaining in heat. So that's positive. What about QC? You see the arrow is away from the engine. That means the engine is losing QC amount of heat. The engine is losing QC amount of heat. So QC must be negative. Understood? As simple as that. And what about W cyclic? You see the arrow of W cyclic is again away from the engine. Work is done by the engine. If work is done by the system, then it's negative. So W cyclic is also a negative entity. So from these two terms, we can calculate Q cyclic. Q cyclic is nothing but QH plus QC. Q cyclic is comprised of two terms, QH and QC. And you see QH is positive and QC is negative. So after sign correction, this becomes mod QH minus mod QC. As simple as that. So what are you getting? You see, this W cyclic and Q cyclic has to be substituted. What is the value of W cyclic? Minus mod W cyclic. You put minus mod W cyclic in place of this. And what is the value of Q cyclic? The value of Q cyclic is given over here, mod QH minus mod QC. So plus mod QH minus mod QC. So this is all about W cyclic plus Q cyclic. I have found it. And the right hand side is equal to 0. So this is equal to 0. So from here one can write mod W cyclic to be equal to mod QH minus mod QC. Okay. Okay. So what should be the expression of eta? So what should be the other expressions of eta? You see, what should be the other expressions of eta? You have already found eta to be equal to mod W cyclic by mod QH. By definition, we know that eta is equal to mod W cyclic by mod QH. By definition, we know this. Now you replace this mod W cyclic, by mod QH minus mod QC. So you replace this mod W cyclic by mod QH minus mod QC divided by mod QH. That amounts to 1 minus mod QC by mod QH. Okay. Okay. So far so good. Very simple. Very simple. Very simple things. So let us summarize. For an engine, we apply Kelvin Planck statement and we find eta to be equal to mod W cyclic by mod QH. Also, we know that mod W cyclic is equal to mod QH minus mod QC. Now from here, if you apply this expression or you plug in this expression of mod W cyclic over here in the fundamental definition of eta, and if you replace mod W cyclic by mod QH minus mod QC, then you get 1 minus mod QC by mod QH. Now it's very clear that mod W cyclic is positive. Mod is always positive. So this is positive. This is positive. So positive by positive makes eta positive. So eta is always positive. Also, from here we know that mod W cyclic is always lower than mod QH. How? Because mod W cyclic equal to mod QH minus mod QC. That means mod W cyclic is always less than mod QH. Mod W cyclic is always less than mod QH because this is a positive quantity, this is a positive quantity, and this is a positive quantity. You are taking mod. And if you subtract one positive quantity from mod QH, you are getting another positive quantity. That means obviously mod W cyclic must be lower than mod QH. It is quite evident from here. It is quite evident from here. So if mod W cyclic is lower than mod QH, then what can you say? The numerator is smaller and the denominator is greater. So obviously this fraction eta must be less than 1, but it's positive. So from here you can say eta varies from 0 to 1. It's positive, so it's greater than 0. And mod W cyclic is lower than mod QH, so it's less than 1. So eta varies from 0 to 1. Okay? Okay? So this much we can interpret in context to an engine. Now, in the next part of our lecture, we would move on to the exploration of the reservoir, to the refrigerator. And that will be discussed in our next lecture. So bye bye for now. Have a nice day ahead.